All right, I think we'll go ahead and get started. Professor, I don't know if you want to speak now since you have to get out of here.
I can, yeah. I need to leave in 15 minutes. Maybe you can introduce
Okay.
yourself and the club, and then maybe I can say a few words. Yeah.
Okay. Yeah. So my name's Hal Owens. I'm the president of the Quantum Game Club. And today I'm going to tell you guys a little bit about our club, what we can do for you all. Then I'm going to introduce you a little bit to quantum computing, and then I'm going to hand it off to some of our past members to present their projects that they worked on over the summer. So first of all, our club officers. So as I just said, I'm the president. I'm a bachelor's in computer engineering. I'm going to be graduating this December. And our treasurer is Hamza. He's a second-year PhD student in Professor Hosseini's quantum optics lab. So he does experimental quantum physics. And then Dongyang Lee is our club representative, advisor. Yeah, so he's the person you should contact if you have any administrative questions about the club. And he is also a PhD student. He's co-advised by Professor Hosseini and someone else. I'm not quite sure. So what is the Quantum Game Club? Well, the Quantum Game Club was founded just this year in January. And its goal is to create and foster an environment for students to learn about and create quantum computing projects. So we do this in a couple of different ways. First of all, we provide educational materials in the form of lectures and YouTube videos. So a lot of times when we're going to have these meetings, the plan for the future is that there will be some time set apart for me or someone else to give you guys sort of an overview of some topic in quantum computing. And then we also provide funding for students to create their projects. So I'll explain that a little bit more. But as an example, over the last summer, there were 8 students who worked on 3 different projects that they all proposed together. And each one of them received a $1,000 grant to work on that project over the summer. And then the last thing we do is we connect you guys with our corporate sponsors. So we're sponsored by QCI, which stands for Quantum Computing Inc., and Microsoft. And with your involvement in the club, you're going to have opportunities to interact with some of the employees. And they're like, for example, over the summer, I know Anderson, wherever he is, he worked on a problem, and he ended up working a lot with someone at QCI on trying to solve that problem. So the Quantum Game Club was founded by the Purdue IQ Park Initiative, which stands for Innovation in Quantum Pedagogy, Application, and its Relation to Culture.
Why are you laughing?
Culture is funny.
So this is the overarching organization that's responsible for the Quantum Game Club. It's a organization that was founded by 3 professors here at Purdue, Professor Hosseini, also Dr. Erica Carlson of the physics department, and Dr. Mushin Mensky of the engineering education department. The goal of this organization is to create quantum education initiatives. So I believe one of the first things this organization did was to found the Quantum Game Club. So going back to the student summer activities, there were 3 different projects that our students worked on. So Hattie and Lawal, who are back there, they worked on the quantum prisoner's dilemma. And then Zureg, Ganga, and Yunlin, Yunlin, Zureg are here. Ganga couldn't make it. They worked on a quantum generative art project. And then Anderson, Ritwick, and Sumin worked on a quantum shortest path game. So if you're interested in learning a bit more about those, you can check out our YouTube channel, or you will also just get to hear about those later in this presentation. So how is the Quantum Game Club going to benefit you guys? So first of all, you will potentially be funded to develop your ideas. Second of all, it opens the door to internship opportunities in quantum computing. So interacting with these companies gives you the opportunity to network with people there and potentially be hired there later. And it's also an opportunity for you to learn about the rapidly developing field of quantum computing. So an example of the way that this club can benefit you is last summer I had the opportunity to work in the Microsoft Quantum Computing Research Division, and I completely owe that opportunity to the connections that were provided to me by this club and by Professor Hosseini. So these are the kind of doors that this club can open if you're willing to get involved.
So yes, again, hello everyone. Thanks for coming. My name is Nadia Hosseini. I'm a professor in ECE. My background is physics. I'm a quantum physicist. I do experiment in quantum. and I'm in ECE now. And so yes, the idea of this IQ Park was to create some platform for students to get involved, learn about quantum technologies and various quantum concepts. And the Quantum Game Club specifically, we are focusing on quantum programming. So we wanted to create this student community and provide as much resources as possible so you can learn, you can contribute to quantum programming. And there are many incentives, as Hal mentioned. So we can provide funding, whether it's a summer scholarship, for example, or we can link you with leading industries such as QCI, Microsoft, INQ, if you are interested to continue working in that direction. But I think this club is for you if you think that Purdue's courses do not challenge you enough. Right? So there are a lot of interesting things you can do here. And we are tackling a lot of open-ended problems and questions in the field. And you learn from that, you can contribute to that. And you get paid for that. Not much, but it's just a little bit that will provide some incentive for you. So Hal mentioned about this scholarship, $1,000 during the summer. The student worked online, wrote program, discussed within each other, learned from each other. But apart from that, we also paid for using this quantum hardware. Using quantum hardware can be very expensive. Like if you want to run a simple program, it could cost you more than $1,000. But we are paying for that as part of this this activity, this basically initiative. So you don't need to worry about that part, how much you want to use quantum hardware. You can use as much as you want. But the idea here is to work with each other, learn from each other, develop some open source programs where others can contribute to that, add to that. It could end up being a game that other people can play. It could end up being an art. These are two examples we did this summer. But we could take it a step further and apply that algorithm, that software to solve some interesting problem. It could be related to a stock market. It could be other things, right? So it's open-ended. It has application in various fields. In many cases, we don't know what those applications are. And the point of this club is to brainstorm, bring people from different backgrounds together to think and see what could be these applications. Again, if you go back to this, the reason we call this IQ Park is a reference to Xerox PARC. That was the place where a lot of personalization of technology, digital technology was shaped back in mid-20th century, right, in 1970s, 1980s. And the idea here is that, yes, we do have some quantum technologies, we do have access to quantum computers, but what do we do with that, right? And the answer here is at least the approach we are taking here is by bringing people, not just physicists, not just engineers, but people from different backgrounds to see how they can use it, how they can apply it to something that they are interested in, right? And it could end up being something super interesting. Maybe not. Your effort could lead to an IP. And again, we will support that. And again, there could be many different things that you can do with it. But and at some level, you can do some abstraction. You do not need to have any quantum mechanics courses. This summer, we had freshman students, second year, third year students, undergraduate students with no background in quantum. They basically worked together, they learned from each other and wrote a program that they are running on Microsoft quantum hardware. And our intention here is to expand that community, expand those projects or define new projects, something that you are interested in. And we try to support that as much as possible. And as Hal mentioned, like he had opportunity to go to Microsoft, and similar opportunities could appear later, maybe next year, whether it's Microsoft, whether QCI, or there could be other interesting problems you can tackle. Again, in case of Hal, he co-authored a journal publication with my group, with Hamza and others, that was published in Scientific Report, which is a Nature subjournal. And he's writing another paper that he's submitting as well. And he does a lot. He is doing a lot of things, both in the experiment in the lab, and also programming. He makes videos. He has on YouTube channels. So there are a lot of things that you can do depending on your interest, your background. You can basically contribute to various activities that we have, and we try to support that as much as possible. Any question I can answer before I leave? I'll try to jump into these meetings once in a while, but if you guys need to talk about anything, just send me an email. We can set up a meeting and discuss that. And Hal is here. We have Dang Yang, we have Nicholas and others who can help you guide through the initial steps to get you to a point where you can start interacting with this software. But if you're not sure what you want to do, maybe you can just join these meetings for a while until you can crystallize some idea that you would be interested to work on. Anything I can tell you about myself or about the idea behind this? Or I think I understand that some of these, if this is your first time coming joining this club, some of these are not clear. You don't know what we are talking about. What do we mean by quantum programming and all of that? And these are things that Hal would talk about. And you can go to our YouTube channel and learn about a lot about those, about why quantum technology, right? If you haven't heard about that already.
At some point.
Which angle should I be from?
Cool. And what I found interesting is that in the past, we group of students from different backgrounds. Like there was one from physics, one from chemical engineering, one from electrical engineering, and they teach each other. They talk about problems they are interested in their own field, and they learn from each other. And they are able to look at these problems from a very different angle. And that's actually what we think innovation could appear. So that's why we want broad background. We want this spectrum. And don't be intimidated if you don't know some of those concepts, some of those physics. You don't have to. Actually, we just want some of you to know that, so you can bring a different perspective to this. And to some extent, this is a learning exercise, but the main point here, we want you to have fun. We want you to do something you are interested, you are excited, so you drive this forward, you push this forward, right? This is not a class, this is not a project. This is something that you define. The project could be something that you define. The group members could be something that you would pick, and you can try to push this forward.
Awesome, thank you. So now I'm going to talk a little bit about what our plans are for this semester. So last spring, we kind of were, for lack of a better word, a bit disorganized. We're a pretty new club, and yeah, we're trying to kind of find a structure that works for club meetings. But really, when it comes down to it, I kind of want it to be something that we collectively decide on. So I think things will change as we see what works and what doesn't. But what I'm thinking right now is that going forward, we're going to have some of the past students that worked over the summer kind of take on leadership roles. So they're going to hopefully be involved with working with you guys to propose new projects and leading those projects and providing some mentorship to some of you guys who don't know anything about quantum computing. And then the plan for the structure of the meetings is that we're going to dedicate about 10 to 20 minutes at the beginning of every meeting to give some presentation on a topic in quantum computing. And then after that, maybe we'll have some small presentations given by the groups who are working on projects to discuss current progress and what they've learned and things like that. And then the rest of the meeting will just be free time that will let you guys kind of socialize and talk about your projects with each other. Just learn about quantum computing from each other. Okay, so now I just want to introduce what quantum computing is. So I'm sure some of you guys have heard of it. You've probably heard something like, oh, qubits can be in a superposition, so you can compute tons of things at once. So that's a terrible analogy. It would serve you well to completely forget that. Quantum computing is really just a fundamentally different way of processing information. By encoding information in quantum states, there are certain things you can do to manipulate these states that would not be possible or is not possible in any kind of classical setting. And for reasons that we don't really understand, these properties allow us to perform certain computations much, much faster. So where is the field at? Well, currently quantum systems today are pretty small. However, a lot of companies like Google, IBM, Microsoft are pouring like billions of dollars into developing functional quantum computing systems. And in fact, in 2019, Google announced that their Sycamore processor that they developed was able to perform a calculation that would take a supercomputer thousands of years. So there's, first of all, that problem that they solved was actually completely useless. And the second thing is that recently, I think a Chinese group published something about how they had came up with a more efficient way to simulate that problem, and they could actually solve it in about 10 minutes on a supercomputer. So it's a race right now between quantum computers and like researchers, but still an impressive fact. In 10-ish years, they've managed to build quantum computers that can compete with supercomputers in useless problems. But anyways, we're getting there. Yeah, so some scientists believe, though, that we are on the cusp of like a quantum era. And they think quantum computers are really going to revolutionize a lot of fields. And there's a lot of reason to believe that we're going to see commercially applicable quantum computers sometime within this decade. Okay. And then, yeah, so this is just a dedication. So the IQ Park organization is sponsored by the DoD. They were created from a grant. So that's that information. Yeah, so quantum computing is all about manipulating quantum states and using their unique properties like superposition and entanglement to perform certain computational processes much faster. So what do I actually mean by this? Well, let's imagine we have some function, f of x, right? And you give it an x, and after some time, it just computes an answer. You could conceivably make a plot where on the x-axis, we have the size of x. So for example, if x was an array, it would be the length of that array, or if x was a string, the length of that string, right? And on the y-axis, we could have the time to completion. So it turns out there are a handful of problems where the best known classical algorithm for solving that problem has a graph that looks like this. And the reason people are so excited about quantum computing is because there are known quantum algorithms which have graphs that look like this for these same problems. So as you can see, once the size of x gets really large, this gap becomes immense. Whereas on a classical computer, this quickly becomes completely uncomputable. It stays reasonable as you increase x. So over here would be called, this would be the like domain of quantum supremacy. Once we can have quantum computers that can deal with this size of x, they're going to be much, much faster. Unfortunately, quantum computers today are really small. They're about 20 to 100 qubits. So that kind of limits us. That leaves us like right here. So in actuality, that means currently classical computers are faster, but we're getting there. Some of the problems that have this kind of speed up would be factoring numbers. So something like decomposing 35 into 7 and 5. You may have heard of this algorithm. It's called Shor's algorithm. And this is an extremely famous algorithm. It basically started the field of quantum computing. It was discovered in 1993 by Peter Shor. And the reason people are so interested in this one is because a lot of current encryption systems rely on the fact that factoring numbers is very difficult for classical computers. So theoretically, with a functional large quantum computer, you could break modern encryption, but I wouldn't worry about that. The estimates for the number of qubits you need to do that are in like the hundreds of thousands. So we're pretty far from that. Another thing that quantum computers are really good at is searching databases. So you may have heard of an algorithm called Grover's algorithm. So Grover's algorithm is an algorithm that can search an unstructured database in square root of n queries of that database. So on a classical computer, on average, you would have to query that database n over 2 times, and worst case, you'd have to query it n times. Another thing is solving linear systems of equations. So equations like ax equals y, where a is a matrix and x and y are column vectors. So if you're given a and y, finding x. So that is something that shows up in a lot of different fields. For example, it's something that's used in machine learning a lot. So people think quantum computers will have applications in machine learning. And another example would be simulating chemical systems. So there's a lot of reason to suspect that quantum computers are going to be really good in things like drug discovery and doing quantum chemistry. And the reason for this is essentially that when it comes down to it, quantum computers are manipulating quantum states. And it turns out that by manipulating certain it turns out that quantum states, they share a lot of properties. So if you can manipulate one, there's a way to poise that manipulation such that it's basically representing a different quantum system. Yeah, so there's a lot of reasons to believe quantum computers are going to be very applicable in the future when we can finally build them. Now I'm going to ask Hattie and Lawal to present their project that they worked on over the summer.
Hello, everyone. My name is Lawal. This is my Hattie. So over the summer, we both worked on the Prisoner Dilemma game. So I don't know if any of you are familiar with the game, but I'll try to explain what it means classically. So there's already a version of the game, which is classical. So what we try to do is to bring in the probabilistic effect of quantum mechanics into it and see how it can improve the dilemma in the name. So what the Prisoner Dilemma is an instance where you, let's assume a police officer arrested two guys for a crime, maybe for robbery, but they don't have enough evidence to prosecute either of them. So now they have two choices. It's either both of them cooperate and not give any information to the police officer, and then you don't have any information to prosecute them. Then they go to prison for maybe a year. I mean, robbery is crime. Or perhaps one of them snitches on the other, then it goes scot-free. Then the other guy spends, like, let's say 20 years in prison. Let's say both of them, 20 years? Yeah. Sure. So then the other guy, that one is reverse as well. Or perhaps both of them snitches on each other and they both get 5 years in prison. I think that's fair, right? So, I mean, at every point in time, the best decision for them to make is to snitch on each other, because if you decide you want to cooperate and the other guy snitches, then you get to spend 20 years in prison while the other guy spends 0 year in prison. So it sort of like causes a dilemma, and it's a concept called Nash equilibrium in economics, game theory in particular. So the idea behind this project is for us to improve the Nash equilibrium, to sort of like enforces cooperation between them, because if they end up defecting, it's not the optimal choice for them to make, but individually it might be the selfish one for them to make. So
yeah, so the idea is so if each robber acted on their own individual choice, then their best option would be to defect against the other robber, right? But if both robbers think this way, then they'll both defect against each other and they'll both get 5 years in prison. Whereas if each robber had on their own somehow agreed to cooperate with the other robber, they each would have gotten away with only 1 year in prison or with no year in prison. So the idea is by, it's not necessarily the best choice to make. So the best choice for each robber to make is not the optimal choice. Precisely. And we're trying to fix that with the quantum implementation of the game.
Yep. So what we did is this. So
this has to do with the circuit. Maybe we can get into that later. I just wanted to give like a high level overview, but I guess that's the whole presentation.
I think you have to talk about circuits.
Yeah, either way we will. So the idea is, in the classical Prisoner's Dilemma game, you can represent each strategy as just a 1 or a 0, right? So you can take the state of the game, which is each player's move, and you can represent that with a single binary digit, right? A 0 or a 1. But with the quantum implementation, you can use qubits instead. And qubits obviously don't just fall into they don't just fall into 0 or 1. They have a probability of being in either one of those states. And so you can use that probability to actually do some quantum moves. And part of that has to do with different quantum operations that you can do on these qubits. So because qubits obviously have a different nature than a regular bit, you can do different kinds of manipulations to a quantum bit that you couldn't do on a regular bit. And the idea is by mapping the cooperate move on one axis, for example, and then the defect move on another, you can find a lot of different moves in between that have certain effects that you couldn't get with the binary classical game. And so that's pretty much what we did. I don't think there's necessarily any good visuals that aren't super technical, but this, for example, this U over here, that stands for unitary matrix operation. And the idea is by manipulating these two parameters, theta and phi, you can get all the different possible moves or strategies that you can play. And what ends up happening is that in our research paper implementation, which it's a research paper that we implemented, is what I'm trying to say. There is a specific move called a quantum move that you can get by manipulating those two parameters in a certain way. And this is a move that has no classical meaning. It only exists in the sort of quantum space. And by using this move, what ends up happening is that I really wish there was an image, but the idea is what happens is that each robber will look at all of their different strategies. They'll look at cooperate, they'll look at defect, they'll look at quantum. And what ends up happening is that no matter what the other person does, doing the quantum move or the quantum strategy will always be the best strategy for them. And the other robber will think this way as well. And so they'll also play the quantum strategy. But what makes this different than the cooperate strategy is that if both robbers choose the quantum strategy, it is the optimal solution.
You cannot
And
take
so-
advantage.
Huh?
You cannot take advantage in that case.
Exactly.
So, and I mean, to put it in maybe a little more explanatory way, when you think about the classical version of the game, when you decide to cooperate, you can take that as 1. You decide to defect, you take that as 0. But I mean, fundamentally, what quantum mechanics is telling us is there is probability to everything, right? It's neither 0 or 1. So if you decide to defect, there's a factor we call the entanglement factor, which is something we put into concepting. So depending on how much of cooperation you guys decide you want to allow in the game, your strategy is not really going to be 0. There is still a probability to it. So the fundamental part of this is trying to bring in the probabilistic concept into the play. So
Right, I'm just trying to see if there was an image up here. This is actually our proposal for the project that we did over the summer. I'm not sure if this zooms in. Yeah, it's not really zooming in that much, but the idea is that you get a totally different distribution of possible outcomes when you allow for quantum moves to happen. And that's really the main, that's like the secret sauce behind this whole idea. That's what made the idea interesting. And what we actually ended up doing is that we made an actual interface for this. And so we wrote some code using Qiskit. So we're not running this using Microsoft just because there were some issues there with customizing quantum operations. We did this using Google's Qiskit, the library.
IBM.
And no, it's with Google.
Oh, it
It is IBM. Okay. Oh, search here. Yeah. So this is IBM's library in Python, and we made an application for it in an interface. And I'm pretty sure we can just show you that quickly. YouTube video script. It's not here. Anyway, that's the idea.
It's there.
I don't think the YouTube is on the GitHub.
Yeah, it's the last.
Screenshot of the
Okay.
There's no screenshot. No. But anyway, that's the idea. And that's just one of the many types of games that you can do using quantum computing. And so it took a mathematical situation and we turned it into a game and we used quantum. So those are the sorts of ideas that you can do in the Quantum Game Club. At least that's just one of them. So yeah, thank you all very much.
So any questions for us?
Oh, true. Any questions about?
And we have the GitHub proof link. You can check out the codes, and if you have any question, by next meeting.
All right, hi, I'm Anderson, and I'm a junior in aerospace engineering this year.
Hey.
And over the summer, we did the title is constraint optimization, but the actual game is just a maze solver. Because we started the game idea by the pretty famous NP problem, the Kelvin-Salzman problem, where you have to pick the most optimal path from one point to another. And yeah, this is our adaptation of it because we want to make it more interactive and for people to play around with it. And so the first part of our project is that we generated a maze at random every time we start. And this graph looks really complicated right now, but I can go through it, explain it. So this is the random maze that we generated for the sake of simplicity. I chose the 4x4 maze, and you can see that every block we can consider that as a node in a graph. You guys know like the basic of graph theory. So each block meaning representing a node, and the purple and the blue edges, those are the edges connecting the nodes, right? So when we generate the maze, we'll be able to have this list of what are the nodes that are connected to each other and they're not, and what are the nodes that are separated by the blue walls. And after we generate the maze, we'll be able to get this list of the purple edges here, and we label them from 1 to 24 because there are 24 edges between every node. And from there, we'll be able to create a spanning tree. That's what the arrows in the graph is about. So a spanning tree is where we start with one point. That's for this case is the yellow point. We propagate down, going down every path that's possible, every possible edges that's connected. So let's say that starting from the yellow node, we go we go from edge 1 and then to edge 5, because that's the only connected edge to edge 1, right? And then from edge 5, we'll get to edge 8, 9, and 12 that are connected to edge 5. And we continue this all the way down until we reach the ending orange block on the bottom. We will stop whenever we reach edge 21. And then we can convert this idea of spanning tree into linear constraint functions on the right. On the right for you guys. So x1 equals 1, meaning that from this subset of the edges, in this case, there's only one edge that you have to pick one, right? And then let's take a look at row 3. It says x8, 9, and 12 equals 1, meaning that from these 3 edges, there's only one edge that's included in the solution to the maze. And then we construct this type of constraint functions this way, all the way down, restricting that you have to pass through edge 21, because that's the edge. That's the bottom of the spanning tree that you have to go through that edge to the ending node, right? And then we use the same idea, but this time we go from the bottom, from the ending edge, on the ending node, because you see that for the yellow or orange node, there's edge 21, 24, representing the first line of the restriction constraint functions, saying that you have to pick one out of these 2 edges in the correct solution, and then go so on forth. And this is the way how we converted this graph problem, graph optimization problem, into a linear constraint optimization question. And that's what we spent most of our time over the summer trying to figure out how we can do this conversion. And this is a little difficult to see, but different from the other quantum project, we actually use QCI, as Hal mentioned earlier, that we worked a lot with the industry, our QCI industry representative, to work through this problem. And as we talk about here, quantum computing can be really good at solving linear equations. And this is what we did here. QCI, their Python library is called Catalyst. It's a ready-to-go optimization solver using quantum machine. And this is what we did here. So on the top matrix, this is how it's just converting all the constraint functions that we had earlier into a matrix. And on the bottom, this big giant matrix, it's nothing but just a diagonal matrix with ones in the middle, representing that, talking about the cost of traversing each edge to be 1. Because each column represents one edge. It's like our variable in the function. And then once we feed that into Catalyst and through the terminal, we can see that the solution here that it represents, that this is the first line. It says that we will want the variable number 1, x1, x5, 8, 9, 9 and 10, and then 14 and 21. Meaning that that's the Catalyst saying that we want to go through edge 1, 5, 9, 10, 12, and 21 from the beginning to the end. And the cost will be 6, in that we're past 6 edges. And yeah, and that's pretty much what our project was about. And we also worked a little bit with random number generation, hoping that we can incorporate that into the maze generation. But we did not have time to finish all that because this took too long. But this is a possibility for our future, also our project during the semester. And yeah, any questions?
So I'm current junior in computer engineering. So this summer we focus on quantum generative art, which the goal is to find a ways of visualizing data of quantum circuits. As a result, we created planetary systems, which you can see over there, with the sun at the center and a lot of planets with random size and rotating around the sun with random speed. And the data for the speed and the size of the planet is what we generated from a 3-qubit quantum circuit. And we use next page. we use quantum superposition principle and entanglement principle to create a 3-qubit quantum circuit. So basically, superposition principle describes a quantum particle can be in multiple states at the same time. So for example, we can play a particle can be placed at a different energy level. So for example, we use the ball over there to represent as a particle. In a classical systems, the particle can only at one energy level. But in quantum world, the particles can be at any stage at the same time. And for entanglement, it describes two particles linked together in a certain way where no matter how far apart they are, even like a particle here at Purdue and the other in space on Mars somewhere, they can still interact with each other. One particle change will result another change on the other particle.
Okay, yeah. My name is Ganga Jayaratna, and I'm an online master's student in electrical and computer engineering. Yeah, that one, yes. In our project, the goal was to create an art piece from a quantum computer to visualize a quantum concept. First, we started researching some quantum-related articles and found this article by Russell Hoffman. He explains a way to illustrate quantum concepts into Mondrian-inspired art, which is basically based on pure primary colors with horizontal and vertical lines. He used Qiskit to write his quantum algorithm, Qiskit programming language, and Qiskit is actually an open source software development kit for working with quantum computers. It is developed by IBM. Q# is also an open source programming language for developing and running quantum algorithms, which is introduced by Microsoft. In our project, we decided to use both Q# and Qiskit to run our quantum algorithm. As Yulin explained, quantum entanglement is one of the most important concepts of quantum physics. So we try to use that concept to create our quantum galaxy. Can you please go to the next slide? Yeah, let's start with our simple quantum circuit. This is a quantum circuit for 3-qubit entanglement. First, we apply a Hadamard gate to the first qubit, and it gives equal superposition states, and then we entangle first qubit with the second qubit and second qubit with the third qubit using two CNOT gates. As a result, we get this entangled quantum state. We ran our quantum algorithm on a simulator. This result, which is in the left side, gives only 0, 0, zeros and 1, 1, 1 state. This is the ideal situation with no errors. And the right side, we ran our quantum program on R&Q machine as well as IBM quantum machine, and this histogram in right side shows our results. Here we have higher probabilities for 0, 0, 0 and 1, 1, 1 states. However, we also have very small probabilities for these extra states. For example, 0, 1, 0, 0, 1, 1. This happened due to the noise of the actual quantum hardware. So in our project, this noisiness is a good thing because every time we encounter an error state, such as 001 or 110, we created a new planet. So our artwork is more visually interesting with the presence of noise part. As you can see here, this simulator in the left-hand side results, you can see it gives perfect states, and we would not be able to create such artwork using classical computer. After obtaining the dataset from the quantum machine, we used Blender to visualize our artwork, and Siru will continue with explaining the rest of our project with the Blender part. Thank you.
So the idea is that we are going to take some other tool or program to visualize what we have here. And the issue with quantum computers is that it's not capable of being visualized in any way without a separate program. So the program we decided to go with here is Blender because of its incorporation with a Python script. Obviously, you can use quantum computers in you can incorporate quantum computers into other machines and other visualization tools or game engines if you wish. And the one we went with here is Blender due to its simplicity and its incorporation with Python. You can run Q# code through various means such as .NET or we can run it through the Jupyter Notebook as well. So our goal was to visualize quantum computer in a way where we can make a comparison to classical computer. As you previously seen, a classical computer, the simulator is not capable of making a mistake, while a quantum computer here is affected by not only noise, but it's also affected by many other probability-based factors. So our goal was to create a solar system based off the noise that we encountered. If you remember from the last slide, we have a distribution of 111 and 000 along with a few errors, where it's not the combination of either of them. And so every time we encounter an error, our goal is to create a new planet. And before every single error, there will be quite a large amount of 111 and 000, which will either become the rotation speed of a single planet or the planet's size. And so with a bit of change in Photoshop, and we present our final product, the Quantum Galaxy. Now, the code is open source, it's available to everyone. If anyone's interested in making adjustments or using the same code, feel free to contact me or anyone on my team. And yeah, lastly, we would like to thank people on behalf of the entire Quantum Generative Art team. We would like to thank the Department of Defense for National Defense Education Program and the sponsorship, along with Dr. Hosseini for creating this program, and Hao and Dong Yang for supporting us along the way. Thank you.
All right, that is all we have planned for today. Thank you guys so much for coming. Yeah, feel free.